Okay, so 8.2 notes is connecting the position, velocity, and acceleration with integrals. So it says a particle moves along the x-axis with an acceleration of a of t is equal to 12t minus 4, and the particle's velocity is 18 centimeters per second at t equals 2. The initial position of the particle is 8 centimeters. What is the function x of t that represents the position of this particle? Okay, so remember when we were doing derivatives, if we started with the position function, and in this case it's represented by x of t. So off to in the margin, I'm going to just write a couple notes. Okay, so this is our position function. Okay, in order to find velocity, remember that is the same as the first derivative of the position function. And then in order to find acceleration, this was the first derivative of velocity or the second derivative of the position function. So this was our applications when we were talking about derivatives. So now talking about integration, since integration is the opposite of a derivative, we're simply just going to work backwards, which means in order to, if we're given the acceleration, in order to find velocity, we are going to integrate acceleration, and that gives us velocity. And then we can integrate velocity to give us the position function. Okay, so the first part is derivatives. The second part is opposite, which is integrals. So using that information, we're now going to solve number 1. And notice in number 1, it gives us the equation for acceleration. Okay. It also gives us an initial condition for velocity. Okay. And it gives us an initial condition for the position function. These initial conditions are helpful because we need those in order to find c after we integrate. So the first step here is going to integrate the acceleration equation. That way we can find velocity. So integral of 12t minus 4 dt. Okay. Remember, integrating, we add 1 to the exponent and divide by that exponent. So this is 12t squared divided by 2, which is 6t squared. And then minus 4 becomes minus 4t plus c. Okay, we don't have bounds on our integral, so we have to represent some constant c. Okay. And then using that initial condition they gave us for velocity, since this is the velocity equation, because it's the integration of acceleration, we know that the velocity is equal to 18 when time t is equal to 2. So I have 18 is equal to 6 times 2 squared minus 4 times 2 plus c. Okay, that condition is important because now we're able to find c. So 2 squared is 4, 4 times 6 is 24, 4 times 2 is 8, so 24 minus 8, move those off to the other side, and we get c is equal to 2. So we're just using algebra to combine that. Okay. So now what we have is the velocity equation, so v of t is equal to 6t squared minus 4t plus 2. Okay, it wants us to find x of t, which is the position function, so we're going to have to integrate one more time. Okay, so we integrate 6t squared minus 4t plus 2 dt. This becomes 6t cubed divided by 3, so that is 2t cubed. The next one becomes negative 4t squared divided by 2, so that's negative 2t squared. 2 becomes plus 2t, and then we have plus c. Okay. So then using our other initial condition, it says the initial position of the particle is 8 centimeters, which means the position x of t is equal to 8 when time is equal to just this one. What does it mean by initial position? 0. We haven't started yet. 0. So this would be 8 is equal to 2 times 0 cubed minus 2 times 0 squared plus 2 times 0 plus c. Okay, all of those are going to end up canceling, so we get c is equal to 8, which means our answer, which is our x of t, is going to be 2t cubed minus 2t squared plus 2t plus 8. That would be our answer. So typically for these problems, you will have to integrate twice. Just like when we were doing these for derivatives, we typically had to take the derivative twice, depending on what it was asking. Okay, any questions on 1? Okay, number 2 says Mr. Burst is driving across town to Mr. Sullivan's house to play with a new set of Star Wars figures. Mr. Burst's speed would obviously vary throughout the drive, but because he's so cool, he came up with a function that represents his velocity, miles per minute, at any time t minutes since he left his house during the 30-minute drive. It says set up the expressions for the following scenarios and use a calculator to solve. So again, anytime it says use a calculator, you're going to be plugging it into Desmos. So part A says how far is Mr. Burst from his house after 10 minutes? So in order to find the distance, this is the position function, and we're given the velocity function, we have to integrate that to find out this answer. So we're going to do the integral. Oops. And it says after 10 minutes, so that's the bounds from 0 to 10 minutes, okay, of v of t dt. So you would plug in this entire function for v of t, okay, solve it at the integral from 0 to 10, plug that into Desmos, and you get 3.010 miles. Part B says how far is Mr. Burst from his house after 15 minutes? Okay, so we're going to do the same thing, but instead of 0 to 10, it's going to be from 0 to 15. Okay, plug that into Desmos, you get 3.397 miles. And again, you're using that velocity equation that they give us above the graph. Part C says if Mr. Burst arrives at Mr. Sullivan's house after 30 minutes, how far away does he live? Okay, which means instead of doing our integral from 0 to 15 minutes, we're doing from 0 to 30 minutes. Okay, so 0 to 30, v of t dt. Okay, plug that into Desmos and you get 22.824 miles. Okay, so that's how far away he lives from Mr. Sullivan's house. Okay, then it says how many miles did Mr. Burst drive? Okay, so if we're trying to find how many miles, then what we're really trying to find is the total distance. Because looking at the graph here, okay, just because he lives 22 miles away doesn't mean he drove 22 miles. Maybe he got stuck in traffic. Okay, that adds miles to your car. Based off his interesting loop here of his diagram, okay, it looks like he started to drive in that direction, got distracted, maybe made a stop somewhere, and then continued driving some more. Okay, so we know that potentially this could be more than 22 miles. Okay, so what we're trying to find is the total distance, and the total distance is the absolute value of velocity. So I'm still going to do the integral from 0 to 30, but I'm going to do the absolute value of velocity, dt. You plug this into Desmos exactly like this with the absolute value surrounding v of t, and you get 28.497 miles. Okay, so even though Mr. Sullivan lived 22 miles away, it still took him about 28 miles to reach his house. So that leads us to these definitions here, because remember, we've already talked about total distance before, but not in terms of integration. So the first part of this formula here, where it says the integral of velocity, well, the integral of velocity is called displacement. Okay, displacement is referring to a vector. Okay, and remember, a vector has a starting point and then it has a directional. Okay, so starting point A going in the direction of B. Okay, that is different than the integral of the absolute value of velocity, which is total distance. Okay, this is completely different than the absolute value of velocity, which is speed. So really, total distance is the integral of speed. Okay, if you're connecting all three of these formulas. Okay, any questions on 2? Okay, number 3. Said a particle's velocity is given by v of t. The function x of t represents the position of the particle along the x-axis. Find the position of the particle after 3 seconds if x of 0 is equal to 5. Okay, x of 0. So this is giving us the initial value, so where it's starting, which means at time is 0, okay, they are already at a distance of 5, which means whatever answer we get, we're going to have to make sure we add 5 to the end. Okay, so to find the position, remember that is the absolute value of velocity, and we want it after 3 seconds, which means our interval is going to be from 0 to 3. Okay, so starting at the start and then going for 3 seconds. Okay, we represent this as x of 3 minus x of 0. Okay, when we're talking about putting this together, sorry, this should be x of 3 plus x of 0. Okay, so x of 3 is found by doing the integral from 0 to 3 of velocity, which is 4t cubed minus 6t squared plus 1 dt. Okay, integrating that, remember we add 1 to the exponent and divide by that new one. So this is 4t to the 4th divided by 4, which is just t to the 4th. The next one is negative 6t cubed over 3, so that's just negative 2t cubed. And then that 1 just becomes t, so plus t, solved at 0 to 3. Okay, so what we're doing right now is just finding x of 3. Okay, we would plug 3 in, okay, solve for that, and then subtract and plug in 0. Okay, so this would be 3 to the 4th minus 2 times 3 cubed plus 3 minus 0 to the 4th minus 2 times 0 cubed plus 0. This whole thing gives us 30. Okay, which means after 3 seconds, he's at a distance of 30. But since our initial distance started at 5, we're going to take 30, add 5, and we get our answer of 35. Okay, so part B is similar. It says find the position of the particle after 2 seconds if the initial value is x of 1 equals negative 2, which means at time is 1, they're already at a negative 2 distance. So once we find the position, we're going to add a negative 2 to the end. So our interval here is going to be from 1 to 2. Why is it not 0 to 2? Yes, because of that position x of 1. We're starting at 1. We're not starting at 0 like part A above. So I'm going to do the integral from 1 to 2, okay, of the velocity function, so 4t cubed minus 6t squared plus 1 dt. Okay. I already know that that's going to give me t to the 4th minus 2t cubed plus t, but now I'm solving it at 1 to 2. Okay, plug in 2 and then plug in 1 and subtract those values. You get 2. But since when time is equal to 1, we're already at a negative 2, I'm going to add negative 2 to my answer, which gives me 0. Okay, which means after 2 seconds, they moved from negative 2, the starting value, to now 0. So they moved 2 spots. Okay, any questions on 3? Okay, number 4 says, what is the total distance traveled by a particle during the first 4 seconds? Okay, this is going to help us with our bounds. It says if the particle's velocity function is given by the following. Okay, so remember, total distance is the integration of the absolute value of the velocity function. So this would be the integral. First 4 seconds means 0 to 4. Of the absolute value of velocity, so negative 1.5t plus 3 dt. Okay. For each of these, especially when you are calculating total distance with that absolute value, you will have access to Desmos. Okay, just like we did in the beginning of these notes. I would not try to solve this by hand, and I would plug this exactly how it looks onto Desmos. When you do that, you get 6. And so that 6 is representing the total distance of the first 4 seconds. And it doesn't give us any units here, so I'm not able to add anything to that 6. It's saying it's going to go a distance of 6 after the first 4 seconds.